between these two parts. Okay? And let's look at what our algorithm do on this graph. So first, what we can see is that we have clearly a cut here that cuts this graph in two. Okay? And for this cut, the red cut, the value of the red cut is n times n edges between A and B. So you have n squared between A and B. Okay, plus n square edges between C and D. Okay, so the value of the red cut is 2n squared. So let's now look at our sample algorithm, sample-based algorithm. So basically, what will it do? So it will sample some vertex here, some n over 4 vertex more or less, n over 4 vertex here, n over 4 vertex there, n over 4, 1/4. It's not n over 4, I'm stupid. So it will sample some set of about the same size here in each part. Okay, almost with a law of large number, it's about the same size everywhere. Okay, so now what can it say? So for C, what it will see is that here, the vertex here, will have a lot of edges outside, okay, and none inside. Okay. For B, it's the same. There's a lot of edges going outside, but no inside. But for A, it will have, so outside going to A. Okay. For A, here, it will see a lot of edges going there, and about the same number of edges going there. Okay. For the node here, it will see a lot of edgings going to A and a lot of edgings going to B. Okay? Because it's a click here and it's a click there. It's a click between that. Okay? So for B, there is a clear definition of what is outside and what is inside. Okay? You won't put, but for this guy, basically, it is as close to A than it is to B. Okay? And it's the same for D. D has a lot of about the same number of edges going to this sample here than to this sample here. Okay, or inside D, more or less. So basically, what do I want to say is that when you will run this algorithm here, so for instance, imagine that you guess correctly the partition. The best you can do is for any vertex in A here, it will have about the same number of connections with this sample than with this sample. Okay, so more or less what's going on is that A will be split in two parts. One will be put in B, because sometimes it will have more connections with this part of the sample here, and sometimes it will have more connections with there. So basically you will have two parts, AL and AR, about the same size, of about n over 2 vertices here, n over 2 vertices there. Okay? For C, it will clearly be put on the right side, but for D, again, any vertex in D here has about the same number of edges to this sample of D as it has to this sample of C. So basically, randomly, it will either be put to the left side or to the right side. So it will be, again, cut into two parts of size about n over 2. So now let's estimate the value of the cut that we've constructed this way. So now the value of the blue cut is, so basically the blue cut is like that now. We have not obtained the red cut, we have obtained the following blue cut. So the value here is basically the value between AL and AR, Okay, so you have n over 2 times n over 2 edges. Okay, you have a complete bar-particle graph between these two guys. Okay, so this is between A left and A right. You have the complete bar-particle graph between B and AL. Okay, so you have n over 2 times n for the cut ALB. Okay, and you have the same for the over 2, C and D. Okay, so you have n over 2 times n over 2, this is for the cut DL, DR, plus n times n over 2 for the cut C, DR. Okay, so what's the result of that? That's twice n over 4 plus n over 2, which is 3/2 of n. Okay, which is much less, and in terms of constant, it's not up to epsilon to n squared. Okay, so this strategy fails. It won't give us an epsilon approximation.
Shouldn't we have n to the square?
What? N square, yes, sorry. Yep. Sorry, clearly. But it's still less than 2n squared. Okay, so what I mean is that this ratio here will never be close to epsilon, to 1 plus epsilon. Okay? So, and I did not take into account the size of the sampling. Okay, the size of the sample, it did not. So, this strategy will not work. So, the question is, why doesn't it work? Why it doesn't work? Why can I not? The problem is that I've based my decision only on the sampling. Okay? And the problem is that for this graph here, the sampling doesn't tell you what is inside and outside D, and what is inside or outside A. Okay? It cannot tell the difference for A, what is outside and what is inside. Okay? Because the outside and the inside looks the same if you have a sample small enough. Okay? But imagine that instead of basing our decision only on the sample, but on the choice that we've made up to now, then what would have appeared clear after a small number of steps is that basically we would start to see that at the beginning we would put some D on the left side and some over D in the right side. But after a while, we would see that we would have a lot of connection lost. Okay, because if we put D here, as DL grows, the new guys that we will consider will have more and more connections with this. Some of them. Basically, what's going on is that you will put some guys here and some guys there. Okay, and what's going on is that this set, as soon as it's a little bit larger than this one, you will have a huge tendency to put it to the right side. Okay, because you will put more edges. Okay, so as soon as you have one vertex more here than there, you will never put anybody here. Okay, so what I'd like to tell you is that somehow you need to be adaptive. What do I mean by that? I mean that you need, if you just sample, guess the intersection with the cut, with the optimal cut, it doesn't help. Okay? Because here it doesn't tell you which is outside, which is inside. Okay, what's inside? But if you do it adaptatively, that means that if you take into account what the cut that you're currently constructing, then you will find the right cut. You may mess up a little bit at the beginning, but after a while you will be correct. You will suddenly discover that it's much better to put the guys here. Okay? Okay, so it was a long introduction to give you the algorithm. Okay, and to justify the algorithm. So now the spirit that we will have is basically the spirit of the algorithm that we will design is somehow we will sample, guess the optimal cut, and then apply the greedy algorithm more or less. Okay, that is to say, put the nodes to the best side, best current side. Okay? So we could analyze this algorithm, but it would take something like 20 hours. So we will analyze a much simpler algorithm that somehow does that. Okay? And the much simpler algorithm does the following thing. How much time do I have? Okay. So the much simpler algorithm works as follows. Let's say that. Okay. Algorithm. So first, alors, let S be a multiset of T uniformly T vertices drawn uniformly at random with replacement. Okay. I draw a first vertex, I put it again in the set, and I draw a second vertex, I put it again in the set. Okay, I'm allowed to draw the same vertex several times. That's why it's a multiset. In practice, it won't be a multiset with high probability. Okay, but theoretically, it's a multiset. Okay, a multiset of T vertices. So we will choose the value of T later on. Okay, so 2. We guess L, so enter where LR is an optimum cut. Okay, so when I mean guess, I mean you try everything. Okay, you try all the 2 possibilities. So this is when I write guess, I mean try all 2 to the T cuts of S. Okay, but the spirit is that you guess it. It's not a guess; it's an exhaustive guess. Okay, but let's focus on the case where you get it right. Okay? So 3 now, what you will do is that instead of affecting each node one at a time, you will assign the node to the cut all together. You will partition the set of vertices and assign each people in each block together. Okay? So what you do is that for each vertex in the outside the sample, okay, place each vertex V, place V in in VI for I uniformly chosen at random in 1 L. L is a bad choice, K. Okay, so you construct V1, Vk. So this gives a partition of V minus S as V1, Vk. So you partition V minus S into K sets, okay, where each vertex is put in one of these K sets uniformly at random. Okay, you construct K-bins. K-bins, and you put each of the vertex in one of the bins uniformly at random. So basically the situation is the following. You have S here, okay, and then you have V1, V2, Vk. So this is the set of vertices. K is a constant that we will define later on. Okay? Good. And S, you've guessed the optimal partition LR. Okay? So you've got S here, and you've divided, you get the optimum partition here. Okay? Good. So now you have to decide. Now what you will do is that start with A0 equal S enter L and B0 equal S, the intersection of S and R, okay? And we will construct the partition AB and place all the vertices in each VI, either to the left, to the A side, or to the B side all together. Okay? So we start with R, and what we do is that for I equals 1 to K, we do the following. Let for all V in VI, okay, so I'm considering, so here I have VI, and I'm considering a V here, and I will decide whether I'll place it to the left or to the right. So in my algorithm, I have already cut this, all the set before, in A1, A2, so this is A0, B0, sorry, A1, B1, A2, B2, AI minus 1, BI minus 1. Okay? So I've already constructed the cut up to VI. Okay? And now I want to decide whether this V will go to the left or will go to the right. Okay? So for the connection of V with the guys that I've already placed, I can know it. Okay? I can look at the edges that goes to the left side and the edges. I know this number exactly. Okay? But now the question is, how do I estimate how many edges do I have here with L and R? I'd like to be able to estimate that, because I want to place V to the side that will maximize the number of edges that are cut. The number of edges that are cut. Okay? So basically, what can I do? Basically, what can I do is try to use the sample to guess that, to guess this number of edges. Okay? In this example, the guess was correct. we could guess exactly which edges was to the left side or to the right side because the sample is uniform. Okay? What was wrong is that we did not adaptively corrected the fact that we did not use the fact that the cut that we've already made tells us a lot about what we should do next. Okay? We did not take into account that. But for this part, we were quite correct. So how can I estimate that? How can I estimate how many edges do I have with the left part and the right part here?
Maybe you look at how many edges you have with all the eyes before, and you say it's the same proportion.
No, because there is no reason why this should be the optimal cut. Okay, you don't want the error to accumulate somehow. Okay, but you can use this sample here. So how can you guess correctly? How can you guess correctly the expected number of edges you have to the left side and to the right side here? Using the sample. Remember that the sample is uniform and thus this set were made uniformly. So basically what's going on here, what's going on there is somehow representative of what's going on here. Okay? The sample was uniform. Okay, so you've sampled uniformly L and R. Okay, so this is a representative situation of S and R, of L and R here. And here, basically what's going on is that you've partitioned your graph uniformly. Okay, so again, this part is somehow representative of all this thing, and so the representativity of that is correct for this part. So how can I guess the degree of V with L here? Yeah, so what would it be? So let's say that the degree of V with L, with some set L, is simply the size of L with the neighborhood of V. Okay, so I'm telling that the degree of V with L, set L, is simply the number of edges that goes from V to a node in L. Okay, it's the number of W in L such that VW is an edge. Okay, and this number, if L is a multiset, you count it twice if the vertex is present twice. Okay, so what can I say about the degree of V with L? So what do I know? I know the degree of V with the intersection of L with S, because I know the intersection of L with S. I know the graph, I know V. Okay, so this I know. So now what I want is to estimate the degree of V with L. So what should I do? It's exactly what we did in the algorithm before. So what do I need to do? I know that, and I want that. What do I need to do? I need to rescale it. That's it. I just need to rescale it. So by how much? I have sampled S, a set of size T of random vertex in N, in V. Okay, so I just need to rescale it by a factor N over T. Okay, so what I will use this estimate. I will use this estimate in order to guess the correct value of the degree of V with L. Okay? Because since L is a uniform sample, it will sample uniformly L. And in particular, L, the intersection of L with the neighborhood of V. Okay, so this is a truthful estimator of that. Okay, the expected value of that will be that. Okay, so it's not the degree of L with V with L that I want to estimate. It's the degree of V with L intersected with V, large V, capital V plus 1 up to capital VK. So what I want to estimate is the degree of V with L intersected with V1 plus 1 union Vk. So what estimator should I use now? Okay, but maybe I don't have to care about the size of this set. Maybe I can guess the size of this set. What can I say about the size of this set? What is the size of it? It's about what, the size? N divided by k. Okay, you've placed all the nodes uniformly at random in V1 or Vk. Okay, so each node has a probability 1 over k to be in some fixed set. So the size of this set is about n over k. So basically, how many of them do I have here? I have k minus I, such set. So basically, the factor by which I need to rescale is n minus k minus I times n over kn. Oh no, sorry. So I have no, sorry. Sorry. Okay. Okay. Bon. So what do I want? I want to rescale it by k minus I times n over k divided by t. Degree of V L intersected by n. Or if you want, let's do it. Let's decompose it by. It's easier to decompose it. So what do I want to say is that this is basically a k minus I over k fraction of the nodes. Okay. So basically, what it should be is k minus I over k times the degree in the whole graph. Okay? Because this is a fraction of k minus I over k of the nodes. Okay? So the degree of V with that is somehow about, in fact, when I write that, is that this is true on expectation. Okay? It's k minus I over k times the degree of V with L. And we know that this is k minus I over k times n over t degree of V with L intersected with S. Okay? So we will use this estimator to estimate how many edges V has with L in order to decide in which part we will put it. Okay? Yes, exactly. For this part, we already know the edges, so we will use the exact value. Okay? But for the rest, we don't know yet. The only thing that we know is that we have a good sample of L, and R here. Okay? And we will use this sample to say, okay, this should look like that, so I will base my decision on that. Okay? Okay, so let's write it down. No, because it starts from I plus 1. It's k minus I minus 1 plus 1. K minus I. So another way to see it is that if if I equals k, then it's 0. That's good. It's with linear function, there is only. only one line that goes through 0, so that's good. It's, with slope 1. That's good. So let's try to formalize that. So I think I will just write this part there. It will be easier. So let's now write the fourth part. So what we do is that now for all v in outside the sample, let EV be the estimator of the degree of V with L. Okay? So this will be n over t times the degree of V with the intersection of L with the sample. Okay? So E here, EV is our unbiased. Unbiased means that the expected value is what we want. Okay? Unbiased estimator of degree of V with L. Okay? 5. Now start with A0 equal S inter L and B0 equals the intersection of S with R, okay, that we've guessed before by exhaustive search. Okay? Good. Now for I going from 1 to K, do for all V in Vi. Now we will use our estimator of the number of edges that goes to the left part of this cut and to the rather than to the right part. Okay? For all V in Vi, let Fv, it will count the number of edges that goes to the left part. Okay? Let Fv, V, left V, yeah, the degree of V with A0 plus the degree of V with A1 plus the degree of V with AI minus 1. Okay? So this is for the upper part of the cut. We forget about the edges inside Vi. Okay? Vi will be small enough so that we don't care. We will deal with that later on. Okay? And now we need to estimate the number of edges that goes with the left part below. So we use our estimator, EI, and we say that it is k minus I over k, it's 1 minus I over k. Okay? Plus 1 minus I over k times EV, which is our, so this is our estimator. Again, it's unbiased. Unbiased estimator of degree of V with L intersected with Vi plus 1 up to Vk. Okay, so when we've done with that, oh yes, sorry. So we've done the calculation, but now we need to place V. So it's not done yet. So FV is our estimator of the number of edges of V with the left part of the cut. Okay? So now what we do is that we do the following. So if Fv is larger than the degree of V with V minus Vi over 2, that means that if our estimator tells us that we have more edges with the left side than with the right side, then where do we put V? This is the degree of V with the set of vertex where you remove Vi. Okay, everybody but Vi. Okay, because we did not take into account the edges inside Vi, in Fi, in Fv. Okay, we removed it. So now, we look at the number of edges. Do I have more than half of the edges to the left or to the right? So in that case, I have more edges to the left than to the right. Okay? More than half of the edges I have with the outside of Vi are to the left. In that case, where do I place Va? Where do I put it? Where do I put it? If I have more edges to the left than to the right, I put it to the right. And the right is Bi. Okay? B is to the left and A is to the right. Okay? In Fv here, I've counted the edges that goes to the A. Okay? So I assume that A is left. Okay? So what I do here is then I say that Bi becomes Bi plus V. Okay? I place V into Bi. Okay? And else I place V to the left. Okay? If I have more edges to the right, with the right part of the cut, then I will put it to the left. Okay? So now this is done with that. I'm done with all VIs. Of course, I have initialized AI to 0 to the empty set and BI to the empty set, okay? And now what do I do? 5. I output the best. So let A be the union for I from 0 to k of AI, and B be the union from I from 0 to k of BI. Okay? And 6, I output the best AB for over all the guesses of the cut of S. Okay? So here is the cut I have computed with the partition LR of S that I've tried. Okay? And now I output the best cut, like that, over all the possible guesses. Okay? Is the algorithm clear? Okay? So the nice thing about this algorithm is that it's adaptive. That means that it takes into account what we've done already. It does not rely only on the sample. And this is why we will do better than on the example that we did before. Okay, it will solve the problem.
Why it's not adapted even more and resamples every time that's the...
Oh, yeah, because if we would do that, then we would need to do much more guesses. and there is no reason to do it because it's already good. Okay, yeah, we could take a sample for each of the. Well, I'm not sure that it would work. Anyway, the analysis would not work because you need in the analysis to use the same sample. I guess it's important. No, it's important that you use the same sample in the analysis. Okay. So we have 10 minutes. So in 10 minutes, we can try to draw the map of the proof. Okay. So we will just first get to some important lemmas, simple lemmas, that will help us in the proof. Yep.
You didn't say how we choose K.
Yeah, we will choose it with the analysis. Okay? So we will analyze it with K and T, and we will choose the best value for T and K. Okay? So I can tell you that T will be something like 1 over epsilon square, and K will be 1 over epsilon. Okay? But there is no surprise now. So, okay. That's the spirit of it. So, good. So the first thing that we need to do is to ensure that these are good estimators. That these are good estimators, that we don't fail with the estimators. And in order to make sure of that, I'm not sure it's needed. Yeah, I think we don't need it. I think we don't, yeah. Well, it doesn't hurt to do it. No, I think we don't need it. So we will do it only if, okay. So there is one simplification to the problem that we can do. Okay, I'm fairly sure it's not needed, but anyway, it's good to know. Okay. So basically, when you're doing a approximation scheme, you're going from a problem which is MPRI, okay, which has only exponential time solution up to, unless p equals np, okay, or some other stuff, okay. So basically, in order to hope to solve it in polynomial time, you need to simplify it, to simplify the problem as much as you can. So, in order to simplify the problem, you should get rid of everything that does not matter, that will have no impact of the optimum value. So the first thing that you should care, like in a problem like that, I'm not sure it's needed, I think it's not needed, but anyway, it's important. It's that, okay, when will this estimator will be close, will be correct? It will be correct if basically V has enough neighbors in L. Imagine that L, so the first thing that we can say, okay, so imagine that L is about theta of n. So we'll show it in a minute, okay? L is about a constant fraction of the vertices. Why is it so? Remember that we've proved that opt is at least alpha over epsilon n square, alpha over 2 n square, okay? This is what we've proved, okay? So imagine for a while that, so what does this mean? Every vertex in L has at most n edges going outside. Okay? In fact, it's n minus size of L, but at most n. Okay? So, how many edges do you have in the cut? The value of LR is thus at most n times the size of L. Okay? You have L nodes in L. You have size of L nodes in L. Okay? And each of them has degree at most n. So the number of edge that goes from left to right is at most n times L. But you know that this value is at least alpha over 2 n square. So this implies that the size of L is at least alpha over 2n. Okay, and this is clearly true also for right. Okay, so L and R that we are looking for are basically in a dense graph a constant fraction of the vertices. And this is why this sampling will work. Okay, because this sampling will be accurate. Because L is large. L is large, so you can sample a constant fraction of the vertices, you will get the right representation of it. Okay? So now you need to have this estimator to be correct. Imagine that V has a very small degree. Has a degree which is tiny, degree. Imagine that the degree of V is little o of n. Imagine that V has a very tiny degree. What's going on? Then the graph does not exist. Okay. Dense graph means that the number of edges is larger than alpha n square. So alpha is not allowed to be larger than 1/2. A graph is dense. We said that a dense graph is such that the number of edges is larger than alpha n square for some alpha larger than 0. Okay? Clearly, alpha cannot be larger than 1/2. Okay? And especially if alpha is 1/2, then the graph is the complete graph. Okay? So, good. So imagine that the degree of V is less than n, less than linear. Then, basically, the degree of V with L is also very small. And when we will do our sample of a constant number of places, this will always be 0. Okay? It's with probability 1 minus something tiny, it will be 0. So this will not be an unbiased estimate in that case. Okay? For that to be an unbiased estimate, we need the degree to be linear. Okay? But this is not an issue. Why this is not an issue? Because if a node V has degree less than epsilon times n, what can I say about the contribution of V to the cut? V will contribute at most epsilon n to the cut. Okay? So if the degree of V is less than epsilon n, then the contribution of V to the cut is less than epsilon n. So if I look at the contribution of all the nodes of degree less than epsilon n, okay, so the total contribution of the nodes of degree less than epsilon n is less than, there is at most n of them, is at most epsilon n square. Okay? Remember what we said before, the optimum is about alpha over 2n square. Epsilon n square, this is O of epsilon times opt. We don't care. We can lose that. Okay? So we can just erase these guys. Okay? So, in fact, this is an unbiased estimator up to a constant term, which will be epsilon n. Okay? But again, we don't care. We can just erase this vertex. So the first thing that you do is that you simplify you have a dense graph. Okay, but it might not be uniformly dense. Okay, but you just remove all the vertex that have degree less than epsilon n. Okay? It doesn't change the value of the cut by much. And now you are sure that your estimators are correct. Okay? These are good estimators. You can find the value of t such that the estimator is correct. Okay, so this is the first point. And so we proved that the L is about that. We proved that. Okay, so now we are left with the analysis. So basically, what will we prove? We will use a technique which is known as hybridation. What do I mean by that? This is a very important technique that you find in many places when you use a probability distribution. Is that basically, at the beginning, your graph is cut like that. You have the optimum cut, okay? But you only know the intersection of S with L and S with R. Okay? And what you want to estimate is the result of your cut, A and B. Okay? And you want to compare that to that. Okay? The value of this cut, that you don't know what it is, with the value of this cut, which is the output of the algorithm. This is opt, and this is the output of your algo. What you do is that you will mix these two things and just show that at each step you don't lose much. How do you do that? Just cut the arrow in two. Okay. In fact, in K. Okay, you cut it in K part. And you study the following. You study the fact, the distribution where you have here S with R, S with L, A1, B1, AI minus 1, BI minus 1. This is a cut. And here you don't care about these guys, because again, they will contribute to epsilon n square, so you just forget about them. And here, you relate it with L with R, L and R, okay? And you compare it, you compare two things. You compare the distribution, which is, again, L and R here, and the cut, which is AI plus 1, BI plus 1. Okay? BI and AI. Okay, I'll stop here, but I just want to give you the flavor of it. So basically, what you do is that you show that when you move this cut to this cut, you don't lose much. Okay? And now what you know is that the difference of this value with this value is the sum of the difference of each of these things. And this is nice because here you can assume that in both cases you have really the optimum, and here you have really the same thing. Okay? And you just now look at the choice you make here, but assuming you have already the correct optimum here and the partial output of the algorithm here. So you're in a very comfortable situation here. You don't know what the optimum is, but you can assume that it is the optimum. And here you have already, you know that this is the current output of the algorithm. So you're exactly in the situation of the algorithm when it has to decide whether the guy has to move to the left or the guy has to move to the right. Okay? And because you've made this hybridation between the optimum that you don't know and the output of the algorithm, you move from one to the other. It's time to go. Okay.